Hello friends, welcome back to our course Math Essential for Machine Learning, and we were discussing about Hessian matrix. So let's quickly solve an example so that it gives a rough idea that how Hessian matrices are prepared. So say I have a function f of x, y. Remember we are considering now multivariable, okay, and say I have a function e to the power x over 3 and sine of say y. So this is my function. So my first derivative with respect to x, with respect to x, df of dx is nothing but 1 over 3 e to the power x over 3 sine of y. Now y being considered as constant when we are dealing with x, and similarly df over dy equal to e to the power x over 3, and the derivative of sine y is cos of y. Okay, now we would need these two information in order to create our Hessian matrix. Okay, so you can represent it by HF, and as we remember, it's nothing but the second order derivative of with respect to x, second order derivative of with respect to dx dy, second order derivative of dy dx, and second order derivative with respect to dy itself. Okay, so you can straight away compute all these calculations. So the first one is the second order derivative with respect to x. So if I look into this portion here, so it will be 1 over 9, right, and e to the power x by 3, right, sine y. Okay, and the second one, the d square f with respect to, so basically I'm taking the derivative of this one with respect to x now, so it will be 1 over 3 e to the power x over 3, and the cos y remains the same, cos y. The bottom function, again we are doing the derivative of f, I mean this one. First we did the derivative with respect to x, now we are going to derivative of y again. So basically I am taking the derivative of this one with respect to y. So it will be 1 over 3 e to the power x over 3, and this becomes cos of y. And the last term, which is this one, is the double derivative of with respect to y. So basically I am taking the derivative of this one with respect to y. So this becomes e to the power x over 3 derivative of sine y. Okay, so what we have done is a simple example of how Hessian matrix is calculated. Is nothing but we are just keeping a track of all our second order derivative or second order partial derivative, right? All right, so how this Hessian matrix is going to help us in the real world. So let's see a quick example now. And what does it say about our local maximum and local minimum? So for example, I have a function, say f of xy, and say it looks like x square plus y square, and say it would look something like this, right? This is y, this is x. So if I take the derivative of with respect to x, so it becomes 2x, and if I take the derivative of this one with respect to y, it becomes 2y, and if I have to create a Hessian matrix, then I take the derivative of again of this one, then it becomes 2. Then if I take the derivative of the second function with respect to x, so this will become 0. Then I take the derivative of this one with respect to y, then it becomes 0. And then if I take the derivative of this one again with respect to y, this becomes 2. So a very interesting thing you should observe is you can see that this function, when it is positive, right, what you can see is there is a local minimum is when you see they're positive in this diagonal value and 0 in rest of the places. Okay, and if this is true, let's try to inverse this one and try to see again. Okay, so for example, I have another function and that looks like minus x square minus y square. So basically what I am doing is I am inversing the function. Okay, now what do I get is again df of dx is equal to minus of 2x this time, and then df of dy I get minus of 2y. And if I create a Hessian matrix, then I can quickly see that I will get a minus 2, 0, 0 and minus 2. So I can say that if there are negatives here and 0 in rest of the places, then I get a local maxima, right? So this is the maximum for this function. So from the Hessian matrix it becomes quite obvious that my function has a local minimum or local maximum if I just observe the the diagonal values here, right? Very simple and very straightforward. But then that will not be the case all the time, and that we'll see later on in our course, not right now, that these values may not be 0 all the time, or this may not be directly a scalar values. Right now what you're seeing is a scalar value. It may not be a scalar value, rather it might be dependent on some other value. Let me show you a Hessian matrix which will create some trouble for us. So rather than getting a constant value, say I got something like this one, and say 5 and say 2 here. So what you can see is they are not zeros, and this is not a scalar, this is a scalar value, but this is not a scalar value. So in such cases, that means it is still dependent on x. So that means my function can have either a local minimum or a local maximum, and it can create lot many different scenarios. So there we are going to use a concept called trace. I encourage you to go and read more about it, trace of Hessian matrix. Okay, but I don't want to introduce it right now because we did not see any problem that will show up like this. But then once we have the data set, and then it will make more sense, that when we will introduce this concept of trace of Hessian. So you can read about it, but for the time being just keep this in mind that in the Hessian matrix helps us in finding the local minimum or local maximum and the geometry of the function. Okay, so I hope you have learned something new today, and thanks for watching, and please subscribe to our channel.